Hello, welcome back to our modular arithmetic section. In the last video, I introduced the concept of congruence, and we went through being able to figure out problems, what it meant to be congruent to, and to fill in the missing pieces and problems with congruence. So today we're going to expand on that and look at a few operations involving congruence, and then we're going to briefly look at check digits. This video, along with the links that you'll see in the modules, together are very important for this material. Okay, so let's get right into it, because you should already know what congruence means at this point. You should already know how to work with a little bit of modular arithmetic. All right, so addition and subtraction. If you see addition and subtraction pop up when we're dealing with congruence statements, you're trying to find numbers from 0 to 1 less than the modulus to make the statement true. Sometimes you end up with more than one answer, as you'll see with multiplication, but for now with addition and subtraction, your problems, you're going to typically just have one answer. But there are cases where you might have more than one in these operations, and I'll show you when that happens. And when we do this, keep in mind that members of the same modulo class differ by a multiple of the modulus. That will help you a lot when you're trying to determine what answers are possible and whether they are going to fit or be the desired answer choices. Okay, so let's look at some examples that actually come straight from your book. In this lesson that I'm looking at, it says determine what number the sum, difference, or product is congruent to in mod 5. What number is the sum, difference, product congruent to in mod 5? So 5 is your modulus, means you're dividing by 5. And you're trying to figure out what results are going to have the same remainder when you divide by 5. Okay, so first one I wanted to look at, it just says 4 plus 4 in the problem. But that's a sum. But they basically are trying to ask us to figure out what is that congruent to in mod 5. And you might be able to look at that and come up with the answer pretty quickly, honestly. Some of you probably already know, and you're probably like, oh, let me just forward the video. Some of you are probably like, oh, I'm not quite sure. I think I know, but let's see. All right, all you got to do there, since 4 plus 4 is together on one side, you just say 4 plus 4 is 8. And then you just figure out what is that congruent to mod 5. And you're trying to find a number somewhere from 0 to 1 less than the modulus. So it can be 0, 1, 2, 3, or 4. So for this problem, divide 8 by 5 and just see what the remainder is, and then you'll have it. Say 8 is congruent to 3 mod 5. So 3 is the answer here. Okay, same little set of exercises, still doing what number it's congruent to in mod 5. Next they give us 12 minus 5. So we're trying to figure out, what is that congruent to mod 5? Well, 12 minus 5 is 7. And we're trying to look for the number from 0 to 4 that's congruent to. So if you just do a quick little division off to the side with 5 being your divisor, when you do, you get a remainder of 2. So 7 is congruent to 2 mod 5. All right, and then there's a multiplication one, 8 times 9. But right now we're focusing on addition and subtraction, so we'll hold off on that one. We'll just do more addition subtraction. I'll just save the multiplication for a little bit later. Okay, it's in the same section, but all right. Now another little section of homework, it says determine all positive number replacements less than the modulus for the question mark that make the statement true. So here they switch it up a little bit, and they're like, well, what plus 5 is congruent to 3 mod 6? So in this one slipped there, sorry. So in this one they kind of switch it up. This time they give you the 3, which is what we were trying to find earlier, and now you got to figure out what was added to 5 to get that 3. Well, if you think about it, with mod 6, 3 would be the remainder when you divide by 6. So you got to try to think of numbers that, well, when you add, like, first of all, what kind of numbers would give you a remainder of 3 when you divide by 6? Well, 6 by itself would give you a remainder of 0. Well, 0 by itself would give you a remainder of 0. So if you add 3 to it, you get 3. So let me write down some possibilities over here. So 3 would be congruent to 3 mod 6. Then if you add 6 to that, 9 would be congruent to 3 mod 6. And if you add 6 to that, 15 would be congruent to 3 mod 6, and so on. So our goal is to figure out, what plus 5 might give us one of these results. Because 3 is congruent to 3 mod 6. 9 is congruent to 3 mod 6. I'll go ahead and write this down so you have it, so you know what I'm talking about exactly. 15 is congruent to 3 mod 6. So it's 3 more than your multiples of 6, because you want 3 to be the remainder. So what can we add to 5 to get that? Well, to get 3, you could add -2 plus 5. The thing is, they want us to find a number from 0 to 1 less than the modulus. So we have to stick with 0, 1, 2, 3, 4, or 5 here. The directions say that, and then typically that's what they're wanting anyways with these problems. But for 9, we can do that one, 4 plus 5. That one works because 4 is in that range from 0 to 5. 15, I think we're getting too high. Then you have 10 plus 5. Yeah, 10's not in that range of numbers that's allowed. So the question mark here would be the 4. So I looked at the fact I'm dividing by 6. Multiples of 6 would have a remainder of 0, but we want a remainder of 3. So all you got to do is add 3 to your multiples of 6 to see what possibilities there are. So I took the multiple of 6, which is of 0, added 3 and got 3. I took 6 and added 3 to get 9. I took 12 and added 3 to get 15. Out of those, I figured I didn't want to go any higher because I think my numbers would be getting too big. Out of those, 9's the only one that really worked here, because with 4 plus 5 equaling 9, 4 is within the numbers we're allowed. We're only allowed 0 through 5. So there you go. That's an addition one. And then let me do a subtraction one. Like 3 minus what is congruent to 7 mod 9. All right, multiples of 9 are 0, 9, 18, etc. But we're wanting 7. So possible numbers, we could have 0 plus 7, which is 7. And then we could have 9 plus 7, which is 16. We could have 18 plus 7, which is 25, and so on. But I think we're going the wrong direction here, because with the subtraction problem, it has to be 3 minus something. And we want something from 0 to 8 to work here. So we got to think, I mean, we could get a negative on that side, and that's okay. We just want the question mark to be something from 0 to 8. If we went the other direction, 7 minus 9 would be -2. That might be our better direction, because then we can use 3 minus 5, which is congruent to 7 mod 9. Yeah, that'll work. So the question mark in this case is 5. Because -2 is congruent to 7 mod 9. You can check it real quickly by seeing if 9 divides evenly into 7 minus -2. And it does. 7 minus -2 is 9. So we needed something, the result on the left to be something that worked, but we needed the question mark to be something from 0 to 8. So I looked at my possible results over here, where I got the -2, the 7, the 16, and the 25. But if I tried to get 7 on that side, or if I tried to get 16 or 25, my question mark was going to be going into negative numbers. And that's not what I wanted. I wanted my question mark to be something from 0 to 8. So by using negative 2, 3 minus negative 2 is 5. Or 3 minus 5 is negative 2. So that was able to work out. I was allowed to have negative 2 there on the left as my grand total. And then by putting a 5 in there, a positive 5, I was able to get negative 2. And positive 5 is within the allowed question mark numbers from 0 to 8. I know that one can take a minute to kind of digest, but there you go for some addition and subtraction. Now multiplication, you're going to have to do a little extra work. Sometimes you're going to get more than one answer depending on how the question's being posed. You might have to replace the unknown with all possible solutions and see which ones turn out to be true. So they might have some multiple results. All right, going back to the one I was trying to do earlier and to change my mind on. Determine what number the product is congruent to in mod 5. This one, there's only going to be one answer. You're just trying to figure out what is that congruent to in mod 5. And you're trying to find a number from 0 to 4. 8 times 9 is 72. There's only one answer that's going to work here. Because as soon as you divide 72 by 5, you'll just get one remainder. And that remainder is your answer. 72 is going to be congruent to 2 mod 5. And you can always check it by making sure that 5 divides evenly into 72 minus 2. 5 divides evenly into 70. Well, that's true. 70 ends in 0. Remember, if it's divisible by 5, it ends in 0 or 5. This one ends in 0, so it's divisible by 5. So that one, you just have the one answer. But if you go to something like this, 4 times what? Notice the question mark now is on the other side in the multiplication part. Now you got to try to stop and think. Try to stop and use all your possibilities and see which one will work. Since it's mod 7, you want to try 0, 1, 2, 3, 4, 5, and 6. Those are your allowed question mark answers. So you can try each one and see which ones work. Well, if you do 4 times 0, that's 0. That's congruent to 0 mod 7. So that one does not work. If you do 4 times 1, that's 4. That's congruent to 4 mod 7. That one does not work. 4 times 2 is 8. 8 is congruent to 1 mod 7. Remember, we want a 3 mod 7, so that doesn't work. 4 times 3 is 12. 12 is congruent to 5 mod 7. 7 goes into 12 one time, remainder 5. That does not work. 4 times 4 is 16, which is congruent to 2 mod 7, so that does not work. 4 times 5 is 20. 7 goes into 22 times with a remainder of 6. So that does not work. And then I'm kind of running out of space, so let me come over here. 4 times 6, the last one. If this doesn't work, then there's no answer. I mean, that can happen. You can have, if there's no answer, it's the empty set. 4 times 6 is 24. 7 times 3 is 21, so you have a remainder of 3. And that's exactly what we want. So question mark is equal to 6. But we had, for the multiplication, we had to go through and test each of the allowed answers and see which ones worked, if any. It's possible none of them will. Then you'd have an empty set, but in this case we found 6. That last thing we tried worked. All right. You could go through and you could try all these, and you might have more than one that works. And that's okay too. Your solution set could have more than one answer. That happens. Not a big deal. So I'm wanting to try another one. I thought I put enough slides in here, but apparently not. I was going to go through those, but I'm going to need those slides for it. So, all right. You know what, let me come back up here Let me do another one in here and squeeze it in. So I really want to do one more. Although that's going to take up a lot of space. Okay, 3 times what is congruent to 3 mod 12? We have to try 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. We have to try everything from 0 to 11, which is 1 less than the modulus 12. Let's see, 3 times 0 is congruent to 0 mod 12. 3 times 1 is congruent to 3 mod 12, so there's 1. 3 times 2 is 6, congruent to 6 mod 12. 3 times 3 is 9, congruent to 9 mod 12. 3 times 4 is 12, so that's congruent to 0 mod 12. 3 times 5 is 15, so that's congruent to 3 mod 12. So there's another one. 3 times 6 is 18, so that's congruent to 6 mod 12. You might notice on some of these that you get a repeating pattern. Not all of them, but this is one of them. 3 times 7 is 21, so that's congruent to 9 mod 12. 3 times 8 is 24, that's congruent to 0 mod 12. 3 times 9 is 27, so that's congruent to 3 mod 12. 3 times 10 is 30, so that's congruent to, it should be 6 mod 12. 3 times 11 is 33. So that should be congruent to 9 mod 12. Yeah. So we had another 3 right there. So all the ones with 3 are what we wanted, because in the original problem it had a 3. So your solution set here includes 1, 5, and 9. All 3 of those work in this particular problem. So you can have more than one answer, or you can have no answers if nothing works. All right, so that's a little bit of the multiplication. One of the practical applications for congruence and for these operations that I was just showing you includes something called check digits. So I'm going to finish up this video today with some check digits, and then the next video I'm going to make is going to talk a little bit about cryptography. So you'll have to come back if you're more into the secret code kind of life. But I want to talk briefly about check digits, and then there's going to be a lot more available in the modules from beyond this, what I'm going to do, the one example I'm going to do here in this video. But check digits are used in identification numbers to help make sure to keep identification numbers accurate in processing. Identification numbers can be numeric or alphanumeric. Numeric means they just have all numbers. Alphanumeric means they have letters and numbers. If they're alphanumeric, then the computations for the check digit involve taking the letters and converting them to some kind of numeric equivalent, and then using that and then doing your computations. So many of them have this check digit built in, which helps avoid transcription errors. So if somebody's copying down a number, this helps to catch an error before it gets too far. Or if a computer is scanning a code, like a QR code or UPC code, the built-in check digit helps to make sure the computer scanned it properly. If it doesn't get a good scan, then there's usually some kind of alert telling you to scan it again. So that check digit helps with that. But the scheme or formula for the check digit that the computer's running through as it's scanning your item often involves modular arithmetic. Some examples of such ID number schemes. I mean, I mentioned your UPC codes. Everything you buy at the grocery store has a UPC code attached to it. Those have a check digit scheme. And one of the links on your modules talks about the UPC codes, and also gets into a special kind of UPC code with the post office. When you get your envelopes in the mail, there's a little barcode on the bottom after the mail's gone through the system, and that barcode also has a check digit involved. The scheme, though, is different than the grocery store check digits. If you buy a traveler's check, or if you go to Europe and use a euro over there, which not so much in England now, I guess, because of Brexit, but in the rest of Europe. So outside of the UK, you have the euros. They have mod 9 check digits. Airline tickets, their numbers have a check digit built in. FedEx and UPS, their tracking numbers. These all involve Mod 7 check digits. The vehicle identification number in your car or truck, that has a Mod 11 check digit built into it. So if you'd like to know more about those, you can either view the links that I provided, or you can also Google some of these and you'll find plenty of information about them if you're curious. But I just wanted to do one example with you so that you could see how an example works. I'm going to do one that involves a U.S. Post Office money order. So if you go and buy a money order at the post office, you'll have an identification number on your money order, and it has 10 digits plus an 11th plus a check digit in the 11th position. So it's technically 11 digits. The 11th position is the check digit part. And usually with these ID numbers, the people who assign them, usually the numbers themselves have some kind of meanings. Like your post office one, if you read about that more, the numbers in there identify your zip code, part of your home address, and some other details that are important to them. Anyhow, so for this particular one, check digits in the 11th position, and this is a Mod 9, Modulus 9 scheme. Okay, so Mod 9 check digit. So basically, what should happen is that your check digit, whatever your check digit is, it should be congruent. So the 10-digit number should be congruent to the check digit Mod 9. Okay? So let's say that we have a money order with 2995 709918. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's the 10 digits. And what is the check digit? You could take this and divide by 9 to see what the remainder is. Okay, I'm going to, let's see here. 9 times 3 is 27. 2, bring down the 9. 9 times 3 is 27. 2, bring down the 5. 9 times 2 is 18. 7, bring down the 7. 9 times 8 is 72. 5, bring down the 0. 9 times 5 is 45. 5, bring down the 9. 9 times 6 is 54. 5, bring down the 9. 9 times 6 is 54 again. 5, bring down the 1. 9 times 5 is 45. 4, bring down the 1. 9 times 4 is 36. 5, bring down the 8. 9 times 6 is 54. And it looks like it's a remainder of 4, but I think I lost track there. Sorry. I was trying to do this in my head, but that's not working, is it? 29, 18, 72, 45, 59, 51, 68. Oh, I went too far. That's what happened. Sorry. And then it should be, what, 9 times 7 is 63. And then remainder 5. But as always, I like to double check, so I'm going to see about doing this on my calculator, if it lets me. 332856657, and then 6 2/3. All right. 3285667, and then that times 9. Yep. Okay. So there I have it. So the 5 is the check digit. That's your answer. So this post office money order would have all that whole string of 10 digits plus a 5 on the end. Now, if somebody was typing in that identification number and they missed a digit or accidentally transposed 2 digits, like switched them, or accidentally wrote down the wrong digit somewhere, that check digit won't work. So it'll help catch the mistake, and then the computer can be like, try again, that kind of thing. So that's really helpful. Now, when I did this, like, you could do this on your paper and you could do the long division, and that's kind of what I was trying to do in my head. And notice it's, long division with that big of a number, it's easy to make a mistake, which I did at the end there. I lost track of where I was, and that I accidentally used one of the digits twice. Well, I caught my mistake after I checked, but still, it'd be nice to avoid those kinds of mistakes. And with Mod 9, this is unique to other moduluses. This doesn't work for like Mod 6 or Mod 7 or something, but Mod 9 is pretty cool. You can see what your remainder is by adding up your digits and seeing what's happening. Like, you can take 2 plus 9 plus 9 plus 5 plus 7 plus 0 plus 9 plus 9 plus 1 plus 8, and you can see what that total is and divide by 9. And then the remainder for that would be the same as the remainder for that original number. This works pretty well for 9s. So we get, what, 59? And if you divide 59 by 9, 9 times 6 is 54, and you get a remainder of 5. So that's a lot faster than trying to do the long division, like what I just did in my head a minute ago. And it's a lot easier to catch, like, not make a mistake. But that's not all. It actually gets easier than that. You can also, instead of adding them all up, you can take your digits and you can cross out or eliminate all the ones that either add up to 9 or a multiple of 9. And whatever's left over will tell you your remainder. I don't know if any of you ever learned this anymore, but when I was in school, we learned how to check our addition, subtraction, multiplication, and division problems by a method called casting out 9s. And this principle is what allowed that checking method to work. I can take this right now, and I can cross through everything that adds up to 9 or a multiple of 9. So really quick, I can eliminate like the 9s and the 0s. And then, like what I have here, I have an 8 and a 1 that add up to 9. And I have a 7 and a 2 that add up to 9. And then whatever's left either will add up or be your remainder. So that can be a really quick way to check these kind of Mod 9 schemes. And I think that's really cool. 9s are really fun to work with because of tricks like that. But anyhow, I've probably taken up enough of your time with my stuff that I like. But I wanted to show you that. I wanted to show you an example of a problem with a Mod 9 check digit scheme. And again, go ahead and make sure that you view the links in modules. Write it in red because it's important. Because there are several links there that will go further with all these concepts. It'll tell you more about barcodes, check digits, etc. There's also an assignment in there that you want to view, because your final exam will have a couple of questions similar to what you'll see on that assignment. The assignment has problems and answers already, but you'll want to make sure you know how to do the problems and get those answers. But they all have to do with check digit schemes. So make sure you're doing that. In addition, it's like a paper and pencil assignment, and it's not on my math lab. But make sure you're familiar with all of that too, in addition to this video and in the book in my math lab, because it goes a little bit beyond what's in your book. Okay? All right, so I hope you enjoyed this. I hope you, when you're looking around now, after you've learned about barcodes and stuff, maybe you'll be thinking about it as you go to the grocery store and check out. And you'll truly realize math is everywhere. Just we don't have to think about it often on a daily basis because there's people who program computers to think about it for us. But it's my job to expose this to you. So anyways, there you go.